Thank you for joining this presentation, and the project we will present today is called VISA 5G Vendor Independent Substation Automation over 5G. This project aims to demonstrate how 5G technology can be used in substations and smart grids with high requirements for operational reliability and low latency. And specifically, the focus has been on creating an automation solution for substations where time-critical protection control functions can be moved closer to the operational site through edge computing in combination with 5G. So today's agenda, I will walk you through the key aspects of our project. First, I will just give you a brief introduction, providing context for the challenge that we've been addressed in this project and the goals we have aimed to achieve. Next, we will look at the system architecture and the requirements that have guided our design. And this includes both technical constraints and operational needs that have shaped the overall solution, so to say. After that, we will move on to the research technology and development. There we will highlight the research progress being made throughout the project here at LTU. We'll then continue with demonstrations and field tests, and here you will get a presentation about the activities being done and how the technology has performed both in controlled environments such as at LTU testbed, but also in a closer to real operation setting at Vattenfall. Following this, then we will summarize and discuss the preliminary key results and insights that indicate some benefits and possibilities of substation automation over 5G. Since the project is not ended yet, it ends on December this month, we will, of course, deliver additional results as the analysis part is finalized. So we are in the work of doing this. And in this part, we will also focus on what we have learned throughout this collaboration. We have been working together for 3 years, and we will talk about what the impact the work has had so far and what the opportunities are for the future. And then finally, we will end with a question and answer session. So the audience is free to ask questions, and we will discuss any of the topics more in detail. So about the project structure, the project started in January 2023. And it ends in December this year. Project is financed by Vinnova and has a budget of a total of 14.6 million, I think it is. I think it says 14.8, but something's wrong there. And the main expected results from this project is to carry out 2 demonstration scenarios. And one has been at LTU in our 5G test environment, North Star, and then at the operational substation environment operated by Vattenfall. And the partners in this project and the consortia have been Vattenfall, Hitachi Energy, Ericsson, Telia, Metrum, IETV, and then Luleå University of Technology through Central Distance Spanning Technology. So, but before we start off, I would like to give you a short background, and then we will let our industrial experts and researchers in this project present their work. But to begin with, we can acknowledge that with 5G it's possible to enable a local private network environment with fast data exchange. So 5G offers high security, low latency, and high reliability, which is critical for the operation and protection of electrical grids, as in this project. And the edge computing allows critical applications to run close to the endpoint, saying that, yeah, close and nearby a substation, rather than solely in a remote cloud environment, and through that provide faster response time and reduce the risks of network latency. By being vendor independent, the system can handle equipment from multiple manufacturers, increasing flexibility, enabling greater potential for standardization. So the project will demonstrate vendor independent substation automation over 5G in 2 scenarios, as I mentioned in the beginning. And the project here aims to contribute to strengthening digital infrastructure for industrial societal critical applications such as power grids and energy transition, and which is particularly relevant for Norrbotten and Sweden's green industrial transformation. Here at LTU, we have the 5G testbed and the innovation program Nordstar, which is operated by Telia and Ericsson. So here we can provide our test environment to this project, and you can access then advanced features such as network slicing, positioning, and edge computing. So we have these benefits in this project. Yeah, and here a little bit about the goals. So now we're at the part where I will let our researchers present their findings and industrial experts to talk about the architectural requirements, which was one of the first activities that they needed to work on to be able to set the requirements for the solution that we have worked on during these 3 years. Our first presenter here is then Rahul from Hitachi Energy. So I will leave the floor for you, Rahul, to speak.
Thanks, Bjorn. My name is Rahul Gore, and I work as a senior scientist with Hitachi Energy Research. And I've been involved with this project for last couple of years. So as part of my presentation, I would briefly describe electrical power systems, and I would highlight the use cases that we considered for VISA 5G project. Now, as you can see in the first slide, typically electrical power systems, they can be divided in 3 main categories: power generation, transmission, and distribution. So electricity is generated at some specific voltage in a generation plant, and then typically it's stepped up to, say, extra high voltage for transmission, and this voltage is step down to a high voltage at sub-transmission level, and after reaching to distribution area, the voltage is further reduced to medium voltage for distribution. And finally, if the load point is a consumer or a commercial consumer, the medium voltage is stepped down to low voltage and delivered to the consumers. So substations play a crucial role in transforming voltages from high to low, or vice versa, and performing various other essential functions between, say, generating station to the consumer. So if you move to next slide. So substations typically include what we call primary assets, and these are nothing but current transformers, potential transformers, bus bars, lines, circuit breakers, capacitor banks, and things like that. And they are usually arranged in switchyard or bays. The basic function of substation automation system in a digital substation can be categorized in, say, monitoring, protection, and control of primary assets. So a typical modern substation automation system has a hierarchical structure consisting of a station, bay, and process levels as described in a figure. The process level is separated from the bay level by a process interface, and this is known as a process bus. The station level of substation automation system includes operator workstation, a human machine interface, and a gateway to the network control center. And this network control center typically hosts energy management system or a SCADA system, which basically regulates the power generation and distribution to consumers. Can you please move on to next slide? So the first use case that we consider for VISA 5G project is process bus, and this is related to communication within substation. So typically the switchyard, as we know, it includes CTs and PTs, and it also includes merging unit, which basically combines voltage and current signals from CTs and PTs and puts what we call process values on a process bus. And these process values or sample values, these are basically fed to intelligent electronic devices or IEDs that typically sit in a bay level, And these IEDs consume these sample values, and they can generate command signals such as a tripping a circuit breaker in case of anomalies in current, voltage, or frequency. And if you look at this figure on the right, uh, traditional substations, typically used copper wires to transmit signals from switchyard to protective relays in the control house. These wires were then replaced by, say, fiber optic based Ethernet. So using a 5G network for digital process bus would simplify substation infrastructure design, and it would obviously reduce the amount of cabling that is needed. Let's move on to second use case. The second use case is line differential protection, and this requires substation to substation communication. So the essential part of power grid is transmission line, and these typically connect the substations. These lines are, exposed and particularly vulnerable to, bad weather or say flora or fauna. So a principle of line differential protection is based on Kirchhoff's law. And it basically says that all currents, into a network node would add up to zero in an ideal condition. So if you look at the first figure, we have two line differential relays. They are basically situated in two different substations connected by a communication network. So we typically have one local line differential relay, and that receives current and voltage data from the other remote IED, and then it takes a decision based on the differential current generated. And if it is beyond certain threshold, we basically generate a trip signal. Um, as I said, we are using a dedicated communication infrastructure between these two IEDs, and most of the times it's optical link in order to have a reliable performance. So as part of this project, we looked at, can we replace this dedicated communication link with 5G network? And this would basically result in sort of removing the installation and maintenance cost of fiber along with other benefits. The third use case that we considered is a teleprotection. Again, it needs communication between substation to substation. So typically, to prevent system failures, a teleprotection system facilitates a selective disconnection of faulty parts by transmitting command signals in shortest possible time. So typically, teleprotection works by receiving a binary signal from the other end, and in conjunction with its local end protection function, it basically generates a final tripping command which can isolate internal faults within the protected line. So one example of teleprotection is basically sharing the blocking signals between two substations. So if you look at the figure, we, for this teleprotection, typically we use a lot of wired communication options. And as part of this project, we looked at, can we replace, this communication medium with 5G network, obviously with benefits such as, we basically get rid of installation, maintenance cost of wired network. Now, in next slide, we basically summarize all the use cases. And if you look at, for digital process bus, we basically connect the switchyard to a Bay Area, and other two use cases, we basically connect to substations. So in case of, in terms of value to customer, basically we look, the complexity and cost reduction of wireless substation automation versus fiber-based likely, do not justify the additional risks in terms of performance and security. In case of differential protection and teleprotection, when we connect substations using 5G instead of, say, optical fiber-based connections, obviously we gain a lot in terms of installation and maintenance cost. And the 5G differential potential here is that with earlier generation of mobile networks, obtaining low latency and security, and many of the features were not possible, and those were which were required for various protection and control applications. And we expected that the 5G would basically achieve some of these control and protection applications. So this is about the use cases that we considered as part of this project. For each of these use cases, we had different communication requirements in terms of low latency, low time synchronization, and also higher network reliability, availability. And also we had a different requirement in terms of EMI, EMC, and environment, and also uh, majority requirements around the cyber security. So that's all about the use cases that we consider. And now I would hand over to Mats for network architecture.
Yeah, okay. Thanks, Raul. So I'm Mats Bergman from Telia, and I work with a lot of our customers with different 5G standalone use cases. I mean, the 5G you have in the macro network, it's more. I mean, you get access to capacity, but not all the new features of 5G with the 5G SA, which is when you really start using 5G, you get. I mean, a lot of new features in the core network of 5G. So yeah, and I mean, the intention with this meeting is to discuss the electricity or the substation part and so on. But anyway, we have a 5G SA network that we are using, and we can either build dedicated radio infrastructure or reuse our public base stations, and we have tried both these options in this project. And we have a lot of other features in this network as well, but that haven't been used here. So Björn, you can move to next slide. So what we mainly been looking into here, and what you will see later on here when we discuss the use cases, I mean, there are some use cases that are really, really demanding, especially these, internal processing bus use cases where you, I mean, that's really, really demanding. But where we are right now with the mobile services and the electrical infrastructure is more like IT type of services. So I guess here it's more, can we move forward into this? And I think we have some promising use cases later on. But we focus on this project, and it's the distribution of the handover of data traffic. Today, the peering points we have in our network is more towards internet services, but then when we come to this type of services, we probably need the regional structure with the, as shown in the middle, the map in the middle to the right, or do we need local breakout from the network? So that's one important questions that we looked into, and the other part is more to get most out of the radio resources, and especially when we work towards public network. Yeah, I mean, you probably have more questions, but I think the focus should be on looking at the use cases and so on. And if there are any questions later on, I can talk more about the 5G network. So that's all for me.
Thank you very much. And then we are heading into the research and technology development. And first off is the electrical power engineering subject here at LTU, and Per Westerlund. So go ahead. You are muted, Per.
I'm Per Westerlund. I'm a senior associate lecturer at the Luleå University of Technology and supervisor of Avis Transme together with Matt Bolan. So what have we done here so far. We have looked at the availability. And what's that? That's how much of the total possible time is this system up and running. And then we have compared wired networks with the radio networks or wireless networks, and also two different networks, topologies, star and parallel redundancy protocol. Availability should be as high as possible, up to 1. Then you have no downtime at all. In order to compare that, we take the minus logarithm of 1 minus availability, so we can, this figure should be as high as possible. And then we can see that for radio network, in this case 5G, we get better availabilities. And the analysis is that we have maybe some more failures, but they are handled faster. So then the availability is better as they are repaired faster. More failures and shorter repair time. If we look at what happens, because what we want is we have some measurements, and then we can see that the voltage or current or the frequency is not what it should be. Then there is some kind of device that decides that that's too high, and then it sends a signal. Please fix that by opening this circuit breaker and breaking all the currents here. So that's why we should look at the total time to trip after a fault. And 50 milliseconds for Ethernet network. Compare that with 20 milliseconds, that is the cycle of the 50 Hertz electric grid. So we get something like 65 milliseconds. So slightly larger, but not that much. A larger difference between a larger spread. And this larger spread should be handled by better buffering. Then we can handle delayed packets on unordered packets. So if they get delayed and then the following one is received first, then we need to buffer in order to reorder them in the order that they should be read. And then we can see that the buffer size must be increased because more things are happening here with Ethernet network. And this is model 3. That means that if there are 2 packets that are lost or delayed more, then the buffer should say, okay, now we need to decide and need to start treating the packets that we have received. But this is an important thing to remember. Better availability. The latency can cause problems, but with a larger buffer, we can handle that. AV has started using some tests with the equipment like this, with Raspberry Pis that are sending out and receiving signals throughout the 5G models and using the North Star. this is to make some other tests than those used that we had in August with lots of equipment. This is in order to see how does North and a standalone 5G network work. Also, we will analyze more of the tests in August. We're looking for how should we set up 5G. There are different settings, as different bands to use, different codings. And we need to think about more what problems will the latency cause. And then we got money from Energiforsk, which is a research company financed by the electric grid owners, to decrease the impact of the delay. And finally, we want to see how we can combine measurement from different stations for better protection. Because now we have solved the communication issues between the substations, hopefully. Thank you.
Thanks a lot. And now we will move into next part and next presenter. And we have Chen Wei online, I hope.
Yes, I'm here. Thank you, Bjorn, for the introduction. So, hello, everyone. My name is Chen Wei Yang, and I'm a senior lecturer, part of the DCC research group. So, for the second research project, we shift our focus a little bit to the overall infrastructure of the substation automation system. So we have two overarching research goals. The first goal is to investigate the feasibility of implementing centralized soft-protection and control for substation automation systems. Specifically, we're looking at whether how we can implement software-driven protection and control system, which enables reusability, flexibility, and also scalability as well. The second research goal is more focused on testing edge-based devices for operating operating protection and control functions over the 5G communication network. And we did some preliminary tests over the North Star network. Can you go to the next slide? So, in terms of our research work breakdown, so our work can be broken down into four main subtasks. So, work tasks 2.2.2 and 2.2.3 are focused on edge protection over 5G, and we have published two peer-reviewed papers on this. Can you go to the next slide? So, task 2.2.1 and 2.2.4 is more focused on centralized software protection. And again, we have also published two papers on this. Can you go to the next slide? So here, I want to talk a little bit about one of our main research outcomes, which is this idea of implementing centralized protection. So the whole idea of centralized protection is that you have a holistic way of implementing the protection and control for the entire substation automation system. So this way allows us a little bit more flexibility in terms of how we can modify our automation systems, and also supports scalability and reusability. We opted for an industrial standard approach, where our solution is based on two industrial standards, IEC 61850, which is the substation automation standards for substation automation systems, and IEC 61499, which is a distributed automation control language. Can you go to the next slide? So how we envision something like this to work is that when it comes to centralized substation and protection, you have a holistic way where you can implement the protection function for the entire substation system. So this gives us the flexibility to actually make any modification we need in the future implementation of the automation system, and only after you have implemented and tested the holistic system, then you can go think about how you want to actually distribute your functionality over different hardware devices. So we think the best way to provide this software-driven reusability, scalability, and flexibility is to try to decouple the software from the hardware itself. Can you go to the next slide? So as I mentioned before, our main underlying technology that we use is based on two standards, IEC 61850 and IEC 61499. So these two standards actually plays quite an important role in our implementation. We have 61850, which provides the standardized communication interfaces and the messaging semantics of how messages are actually passed between the functions within a substation, where 61499 actually provides the implementation of these functionalities. So, so from this overview here, the most important takeaway from this is that we can see that both 61850 and 61499 actually promote holistic design. For 61850, you start with a holistic view of the entire system, where you can define your specifications for your system, and then you define the communication and the message passing or the message semantics between the different functionalities. And 61499 also supports this holistic view of implementing control, and our approach has to be using 61850 to define the communication and the functional requirements, and using 61499 to actually implement the actual functionality to be run on edge devices. Can you go to the next slide? Okay, so here I sort of came up with a step-by-step way of how we could approach in designing such systems based on centralized approach. So suppose that we have a very basic bus protection system that we want to implement the control for. So here we want to test the communication between a feeder ID and a transformer ID to see what sort of speed which we could get for blocking signals between the feeder ID and the transformer ID. So the first step you would do is you define your IEC 61850 communication and the message passing between the different functionalities within your system. So once you have this communication configuration designed, then you go over the 61499 part. So for every functionality you have defined on your 61850 specification, you implement these functionalities in the context of 61499. So here we can see that we have now designed a system which is holistic from the 61850 perspective and 61499 perspective, and also both approach are quite modular as well, which allows us to modify the functionality as we need. So after you have your 61499 automation control implemented, you are then free to deploy these to the edge devices, where we could do, for example, 5G testing of the network. So we did do some testing in the early part of the project, where we implemented this simple scenario over to edge devices, and we did some tests over the local north-side network here at LTU. Can you go to the next slide? So here, once we have a simple implementation in place, scaling up the solution is quite simple. So here we see that we again have a very similar scenario as we had before, but this time we have 4 IEDs. So because we're working from a holistic perspective, it's quite straightforward for us to simply scale up the software part of the solution. Okay, so to support this, we also developed a co-simulation platform where we have a set of 5G enabled edge devices in the loop with our real-time simulator. So the real-time simulator is simulating our power system simulation, well, with the 5G controllers that actually do the protection and the actuation. Can you go to the next slide? So in terms of results in future work, so I can say that in terms of results, we have published 4 peer-reviewed papers. We have also developed a hardware in the loop simulation platform involving our real-time simulator and a few 5G capable edge devices. And we also did some 5G edge device testing of bus protection using the software-based solution. In terms of future work, we want to increase the support of 61850 communication for these edge devices. And we also want to look a little bit more into what sort of role that edge devices can actually play in terms of the protection and control systems. Yes, and this concludes my part.
Thank you very much. Let's move on then. Now we're talking to the industrial experts in this area, which is Vattenfall, and we will start off with Daniel Brodén from Vattenfall. So please go ahead.
Thank you, Björn. So my name is Daniel Brodén. I work at Vattenfall R&D as a senior research engineer. And on this slide, you can see some of the pictures of our demonstrations, lab tests in Luleå on the left side, and on the right-hand side, some of the field tests me and my colleagues have been involved in. But we'll get into the details of that and the results. So we can move on to the next one here, Björn. But just a bit briefly, Rahul touched on this in the beginning of the presentations on the use cases we've considered. So we have 3 use cases, you could say, that we found interesting to evaluate 5G over, and those are related to protection, automation, and control. So as Rahul mentioned, the use case 1, it's process bus using 5G. Use case 2 is line differential protection. So these are the 5G applications that we see could be very useful in a fully digital substation. Whereas the use case 3, which is teleprotection, is very interesting also from when we talk about optimizing network selectivity on existing substations, which are not necessarily fully digital. So these are the 3 protection, automation, and control use cases that we will present some results on. And we can go to the next one. So just a really quick recap, because I think Rahul has already touched on this, but this is a bit of a different view here. You can see the control room, the substation house, and the switch yard. So on the right-hand side, you would have your primary equipment, the process level. And typically, when we talk about fully digital substations, these are fiber connected. So there's fiber connections from the IEDs to the merging units out on the switch yard. And this use case is essentially considering if 5G could be an alternative communication medium to fiber. And these are very highly demanding, time-critical applications where it requires a few milliseconds end-to-end latency. So it's collecting the sampled values from the process level to the IEDs. And use case 2, if we move on to that one, here we're talking about line differential protection, or sampled value-based line differential protection, as we wrote it. And here also, it's to investigate if 5G also could be an alternative to fiber, which is used today for this application. And these first 2 use cases are very, very highly time critical. So we're talking in a few millisecond end-to-end latency requirement here. And we move on to the 3rd use case, which is teleprotection or remote blocking, as we call it, using 5G. Which is closer to maybe traditional substations, where we talk about, we can consider, for instance, a 40 kV radial network, where using goose messages, you can send out a blocking signal to the upstream substation, so that you block the breaker from tripping when there's a fault, so that you instead isolate the fault closer to where it actually has happened. And for instance, on a 40 kV network where there can be cases where there is no fiber connections between substations, then 5G could be an interesting alternative or solution then to optimize the selectivity and reducing the outage, for instance, to nearer to the area where it's affected. So this type of application is not as time critical as the previous two, but we're still talking about the order of like a blink of an eye. So in that scale of time. So these three we will come back to, but I just want to mention also that we have a fourth use case also where we're talking more about monitoring power quality data, high resolution using 5G. And here we have collaborated with Metrum on this application. So I will just mention a bit about that before we dive into the first three use cases. So if we go to the next slide. So we have considered the case where we're installing power quality meters in secondary substations and have them connect to the 5G network for data collection and typically like minute resolution data. So here is a brief overview of like the architecture, you could say, on how this would look like. And if we go to the next slide, here's the actual cabinets that we have installed, which Metrum has prepared. So they consist each of a power quality meter, an uninterruptible power source, so it can run even without if there's a power shortage, a data concentrator to buffer the data, and 5G routers, of course, so that we can then collect the data that's being streamed. And if we go to the next one here, just some pictures from the field where you see on the right-hand side, you see the antennas that we have installed on a secondary substation and the actual cabinets which are mounted inside. And then, of course, we have current transformer mounted on each phase of the substation so we can collect the power quality data. And I believe on the next slide, we have a picture of the dashboard on how it looks. So this is minute resolution data, which has been streaming since July 2025 for a secondary substation. So you can see, for instance, you get the voltages for each phase, the current for each phase, and then you have some power factors, reactive power, active power, and the frequency. And you have the time series dashboard where you can evaluate events where there's power quality issues. So this is what we've done in use case 4. So we will look a bit further into this data moving on, but it has at least worked very well, and we have a lot of almost 6 months of data on minute resolution that we could review moving on. Yes, so that's all for use case 4. So if we go back to use case 1 to 3, the protection, automation, and control. So we wanted to evaluate this in a laboratory environment. We did this at the CDT lab at Luleå Technical University, where they have the Northstar 5G standalone network with local breakout. So we had to put together a fully digital substation, you could say, on wheels. I will show some pictures of that. And we evaluated, so we did this during a test week in Luleå, and we evaluated 5 different network configurations using different cell frequencies. You can see on the right-hand side, so we have 5 scenarios. We have indoor cells and outdoor cells and different frequency bands that we have tried to evaluate the performance for the different use cases. So a bit about the evaluation methods for these use cases. So we've used, to monitor the performance, we've used a network traffic analyzer. So you can see on the right-hand side to get the latencies, but we've also had monitored the network traffic using network captures with the network traffic sniffer during this test week. So moving on, a bit about the test equipment. So I mentioned this, if you think about what Raoul mentioned with the modern substation, this is basically the modern substation on wheels. So you have, on the left-hand side, you have a test rack, which Hitachi put together, which I'll go into a bit more details on. And then on the bottom right side, you have our test rack that we've put together. And then you have some miscellaneous hardware, which different partners have helped us, including the 5G routers, for instance. So this whole equipment interfacing with each other is what consists of our modern substation, digital substation, you can say. So diving in a bit into the details of these test racks, you have our Vattenfall test rack. Here's a bit of a description of what it consists of. So if you remember from the previous pictures with the switch yard, you have merging units. So we use merging units from Hitachi here. So these are the units that collect the analog values from the process side and digitalize them. We have some switches, and we have a voltage and current amplifier, which we use to so we simulate the analog values, and we amplify those so that they can be used in the remainder of the system. So some highlights here. So this is essentially the process level that was described earlier on wheels, and it integrates with the real-time simulator to emulate the analog signals from the instrument transformer and the switchgear operation. And if we go to next one, it's the Hitachi Energy test rack. And there's some different hardware equipments, some communication equipments here, and we have maybe the most interesting here is the line differential protection relays, bottom two here, where we can evaluate the line differential protection functions. So this is essentially enables the communication between the bay level equipment and the process level, which is our test rack from Vattenfall, you could say. And it provides then the evaluations of this line differential protection use case. And then if we go to miscellaneous hardware here, so we have 2 5G routers from Ericsson on top. We have the network traffic analyzer. We have the real-time simulator that we get to borrow from LTU here to simulate the analog values, and some test equipment, basically, which allows us to evaluate the performance, to compare to our requirements, and enable this communication between bay and process level. So that's enough about the hardware. So if we go back to use case 1, process bus using 5G. So we essentially wanted to evaluate the sample value streams then from the process interface unit or the merging unit to the ID. So it's that yellow kind of trail you see on the right-hand side of the setup here. So from the process interface unit all the way to the ID here, going through the indoor cell of the 5G network. And then we have this network traffic analyzer checking the sample values performance at each switch. So I don't know if there's a pointer here, if I can point on the graph, but otherwise, oh, there it is. So if you point to the left switch here on the VLAN 71 there, so it's that one exactly, port A. So that's supposed to be the switch yard switch. And then you have the control room process bus switch on the right-hand side here. There you go. Yeah. And we tested this following the first scenario of the indoor cell on 3.5 gigahertz, basically. And then we also had another setup where we thought, well, can PRP or parallel redundancy protocol, where you basically have two parallel sample value streams for redundancy purposes, if they can compensate for the 5G performance, if you have packet losses or or something like that. And so we performed this PRP configurations for one ID and one processing interface unit, and we evaluated sample value streams here also using the same methods, and tested some different scenarios, the indoor cell 3.5 and an outdoor cell. So if we go to the next one, we have kind of a table summary of these cases where we have evaluations on the first row without PRP, and on the bottom 2 rows with PRP on LAN A and LAN B for different scenarios of network configurations. So what's interesting here, you can see maybe the red bold average latencies, end-to-end latency, I should say. So we average around 20 to 30 milliseconds for this use case, which seems low, but actually these use cases require even less latency than this. So for these particular tests, we noticed that we exceed the requirements for this type of low latency application. So we can move on to the second use case, which is line differential protection. So we get quite similar results for this one. So we get around 20 milliseconds, and also this typically exceeds the requirements as stated by the standards. But then if we go a bit to what actually caught our attention, or we thought was very interesting, it's this teleprotection use case, where we evaluate sending goose messages from the ID here to from one end to the other, basically. So it's this use case where you have you're trying to block the tripping from the upstream substation. So if we go to the test results right away here, we can see on for one of the scenarios here, scenario 1, we average around 16 milliseconds with a maximum latency of 20, and this shows pretty good potential for this particular scenario where we don't have to have a few millisecond requirement. So we were interested to kind of see could this actually work outside the lab environment, because here we had we had a pretty trimmed lab network, I would say, even though there's probably a lot of things you could configure, but we thought this was very interesting to see if this actually works out in the field similarly. So we took out this use case out for field tests. So if we go to the next slide here, so we selected 2 substations on a radial 40 kV network, which had the fiber connection for test purposes then, so we could do the monitoring in a good way. And we performed evaluations on both the 5G standalone North Star network and the public 5G network. Unfortunately, in this use case, in this field test, we didn't have any local breakouts, so perhaps the performances could be even improved if we have all the right configurations. So that makes it that we add some transport delay since it needs to communicate back to the core network in Stockholm and back. We didn't consider any priority slices here, and we had set up that we had status changes each second, basically. I'll explain a bit more about that. And in terms of 5G coverage, it was good, but perhaps not optimal. But we had 2 to 3 kilometers from each base station, and the distance between the substations around 12 kilometers. So if we go to the next slide, so this is a bit the field test setup. So we have the first green box here is station 1. And the second one is station 2, so it's the 2 substations we considered. And here you can see our test track, which we also used in Luleå. which has the process interface units where we generate the goose messages, and we have 2 5G routers that are mounted on each station, and we send these goose block messages, and we have this network traffic analyzer and network sniffer to evaluate the performance latency of when the message actually arrives. So if you go to the next slide here, here we have a bit more about the goose messages that we sent. So here the messages, there's no handshake in these messages. They're not the arrival of the messages are not verified to the upstream substation. So we kind of worked around this by sending messages repeatedly to ensure that the status change occurs. And after there is a status change, for instance, there is a fault here, send the block goose signal. We have a fast repetition cycle, you could say, which is this mean time. And then we continue to send the messages regularly with the max interval time of 1 second, I think. So this is a bit about the test setup, you could say. And here we have the preliminary results from the fields. So these are latency results, scatter plots for both the 5G standalone network and the public network. So the scale, the y-axis scale is a bit different here. But it's in seconds here. So you can see that it's the top one is everything below 50 milliseconds, and the top value and the bottom is 20 milliseconds and lower. So you see that a lot of the scatter dots are in a few millisecond range, but you can see them in the table here down. You see the average ones. We average around 30 milliseconds for both cases, and of course we have a bit different results depending on if we're using the standalone network or the public network. But and then you can see also in the first column how it compares to our lab tests. So I think I would say this confirms our expectations, and we still think this is a very interesting case. So you see, for instance, the field test 5G standalone, we max at 46.6, which is well within our requirements for this type of use case. So that's a bit about the results, and we have some highlights about the conclusions then from our side and benefits. So we see that this 5G standalone shows good potential to fulfill this teleprotection latency requirement. And we also think that this could be an interesting cost and time-effective alternative to fiber installations. So even though it wouldn't work, if there's a case where it doesn't work, there's already a control application for how this is handled today. But it could provide an extra layer of better optimizing selectivity, and instead of building long fiber connections between substations, then 5G could maybe be an alternative which you could set up faster and more cost effective. That's our hypothesis here. And future work. So we have a lot of data. We have only done, I would say, a bit of a shallow first performance analysis looking at latencies, but we could of course dive in more deep into this analysis. So that's what we're expecting to do a bit more. We also talked a lot about time synchronization of hardware using the mobile network. And here, for instance, it would be interesting to explore time synchronization using SIB9. So what accuracy can be achieved, and can it be used instead of the classical NTP or PTP time sync for select use cases. And we will continue analysis of inter-substation communications. Can latencies be further minimized using routable goose? How do we do it when there's more than 2 substations to communicate between. So does it scale well with routable goose? So these are some of the questions that we would like to evaluate moving forward. And of course, now that we have some interesting results, further review the business case for 5G using teleprotection. Yeah, I think that's all, or did I have another slide? No, that's all from my side. Thank you, Björn.
Thank you very much. And now we are approaching the end of this presentation. We are well within time, so we have a lot of time for discussion if we find the opportunity for that. But we discussed a little bit before this final seminar about what key results and insights would like to lift in this presentation, and we have listed some bullet points that we think that we could have a discussion around and lift so that you and the audience understand a bit better about this. We will also have the questions and answers session after this kind of reflection moment. Let's begin with the first bullet point there. 5G SA shows good potential to fulfill teleprotection latency requirements. What remaining gaps is there before we can utilize 5G as a fully trusted protection critical application, for instance?
Yeah, so I mentioned this routable goose. I mean, I think it would be interesting that we do some further test with that. I mean, the first result seems to be that the latencies seem to satisfy our requirements. But then there's certain situations where for instance, a max latency of close to 100 milliseconds could be an issue, depending on the the system configuration and the selectivity plans and so on. So I think we need to kind of dive in a bit more onto the details on the actual, like, what is the actual requirement for specific setups, so to say. And then, of course, the business case is interesting then. I mean, what does it cost to do, a fiber connection between these, and what is the cost of minimizing the outage to closest to the fault? So that comes with the cost-benefit analysis for the DSO to do. So I think here we have some things we could really get into more details and quantify.
Yeah, and we also have a bullet point there about buffering, which comes from the research side of the project. What do you say, Per? What will you explore further in this matter?
Well, then I would like to give the word to Hafiz.
Yeah, thank you, Per. Hi, everyone. I'm Hafiz Kazmi. I'm the PhD student here in LTU, in the Electric Power Engineering group, and have been working with the VISA 5G project for 2 years running. According to the research that we have done and the simulations, and also taking in the results and the latency data sets that we gathered using the 5G network, we've seen that, yes, in terms of the jitter of the network, it's much higher compared to what an Ethernet network would provide, since it's a wireless network. So for that reason, buffering is necessary. In terms of types of buffering, there could be quite a lot of things to think about in terms of whether we would like to have a packet-based buffering, where the algorithm might look into how many packets are there in order to reorder them, or whether it would look for any timeout period where it would only wait for a certain period in order to reorganize the packets in proper sequence. So it's still research in progress, but hopefully there would be some optimization required in order to make sure that we have low latency as well as proper acceptance and reordering of the sample values in order to make sure that the protection is working quite well.
And then we come into the reliability part as well in 5G. So we have something to add there as well.
Yes, as also Per discussed in his slides as well, that we have seen the availability of the system is comparable when we compare the wireless 5G network with the fiber optic Ethernet network. So it's comparable, and also it's a bit higher because now we are eliminating the number of wires. So a lot of wires would not be used, which reduces the amount of failures from the device perspective. However, we have also seen from our calculations that the number of failures are a bit more frequent if we use a wireless 5G network. But the positive side is that the time required to repair is much lower. So that's why it becomes much more faster for it to repair. And so it's quite intuitive that by using wireless 5G network, we are also getting the advantage of scalability as well. So it should be a really good option moving forward, looking into it a bit more in detail. However, the preliminary results show that reliability could be comparable, and in some cases a bit higher compared to wired Ethernet networks.
Very good. From the beginning of this project, the businesses participating here and the partners participating in this project hadn't been working too much in this type of collaboration since before. So, I mean, for Vattenfall, there has been some challenges and even internal challenges within the organization to work with this type of research and in this type of settings. Maybe Daniel, you can mention a little bit about the new insights that you have gained in working in this way.
Yeah. First of all, I think it's been very educational to work with different companies so broadly. But yes, of course, I mean, Vattenfall is a big energy company, integrated energy company, so utilities. So we cover from production, distribution, the whole spectra, you could say. So it's a big company. We have a lot of processes, of course, also. So I mean, it definitely has challenged a bit our ways of working, I would say, at least on the research side. But it's been very, I think, good for us to get also perspective from, for instance, the telecom industry, and also interactions we may have had with the university in this case. So.
Yeah, I mean, just to add to Daniel's point, I mean, see, we come from energy company, and it was highly beneficial discussing, various aspects with network companies and then also with the academic. Yeah. So, I mean, I personally got a lot benefited with these discussions and understanding various issues on this communication and protection interplay. And, in terms of, say, packet loss, what do we mean by packet loss from protection point of view? And then how does it translate to packet loss in a network domain? So there had been a lot of learning from that perspective. So this was highly beneficial to collaborate with industry partners and then also the academic university. Yeah.
And I can just add that I mean, we work a lot with business-driven innovation, but some of these use cases are a bit further down the lines, a bit more visionary, you could say, with, for instance, use case 1, which is sampled values over 5G. So, I mean, this type of setting, we can also look a bit further than around the corner, which I think is also interesting from a research perspective.
Any comments from Telia or Ericsson?
From Ericsson, I think it has been a very successful cooperation with Vattenfall and Hitachi to really learn the kind of requirements and then apply them in reality using our test beds, the Telia North Stars, both here at LTU and at Vattenfall. So I think that has been really successful, and we have really cross-fertilized our competencies. So successful and very committed participants from respective organization, I must say.
Any comments from Mats at Telia?
Yeah, no, I mean, it's been really interesting project to work with, and I think it's I learned a lot about the energy infrastructure, but also I think there are, I mean, it's a lot of demanding applications, but I think, I mean, it was really good that we actually found some applications where it's already, I mean, we could enhance our services that we have, because I think in some sense, I mean, these really demanding process bus applications, I mean, it's probably possible to solve, but I mean, it's also a question about cost, because I mean, you need so much redundancy in the network as well. So no, but it's been very interesting and really fun to work within this project.
Yeah, I would like to add one point to add up with what Daniel said as well. That basically the standards that we are trying to play with here, those are designed with having optical fibers or wired Ethernet networks into the bucket, so to say. So it never was designed for a wireless communication network in the first place. So utilizing a wireless network here, it's like retrofitting something into a standard. So it will have difficulties, and we are looking into something quite farther away now, which we can, in terms of research and collaboration, like what we are having at the moment, we can find new ideas and solutions to make sure that, yes, now the next standard, which might take these sort of conclusions and results into consideration, and then they will design new standards which will incorporate wireless networks into the standards.
Good. Yeah, from a project management perspective, I must say that this project has been really successful and as Mats said, dedicated people, and the field test that we have done has run along really smoothly, and I think we have achieved a lot. And it has been complex task with many people involved. Field tests or the laboratory tests in Luleå involved typically around 20 to 25 people in different roles, and even on distance participating. So I thought that was highly successful, and it was a good thing to showcase that we actually are good here in Sweden and innovative and can work together, which is a strength. Regarding the project management of this project, from my point of view, I wasn't a part of it from the beginning. I took over as a project manager roughly halfway in, or after 1 year or so. And I know that many of the original participants in the beginning of this project is not still around in this project. So there has been some change of people in the project, but still we have managed to keep the momentum in the project and has done great work and fulfilled the goals of this project, I would say. Yes, Per, you had some comment.
Yes, I remember so well the tests in August, and I was impressed, first of all, by the amount of equipment that needed to be brought there and connected. And as you said, we had some online support that was really good from Hitachi Energy. And we have published a journal article about it, and then we got questions. Okay, but you're just doing simulations. Why are you're not presenting some measurement data? And then we explained that, okay, we have not seen so many people using that, the references that we had, and then we also the reviewers, okay, we have planned a measurement together with some industrial companies, but that was delayed. And I think that this was a unique possibility to see how it works. So that it was a great achievement.
Yes. About the North Star test bed here at LTU and also in the field tests, what are your experiences connected to this? I mean, now we have the opportunities to use this network, and it's not a lot of places here in Sweden that we get the opportunity to test stuff in these settings. Any reflections on the North Star network and the future about this? In the standalone functionalities will start to roll out soon in the public society. So I guess we will eventually get to test these in the public network, but there are still some time left. So it's good to have these opportunities to test. And from my point of view, I see that we at LTU have these test beds kind of brings the company and industry closer to us, and we get the chance to do more real-life research together with industrial partners. So from our point of view, it has been really valuable to keep these industrial test environments.
But I think also for our use case evaluations, I mean, it's been essential to do these tests on the standalone networks to see how fast can we get down to, I mean, compared to the requirements. And I understand there's a lot of configurations and things that can be optimized, but at least it gives us some sort of indication, which is interesting.
And also the fact that in terms of cybersecurity for substations, then the standalone network should be the choice compared to like having a public network. So I mean, having lower latency and better protection or security in terms of communication and data protection, I think standalone network should be the choice for industries moving forward to implement 5G into the energy industry.
Yes, potential in deploying standalone functionality on edge devices over 5G.
I think that'll be from me. So I think for us it was very interesting because this is actually the first time we have done any actually testing of our centralized approach with edge devices with 5G. So that was actually very interesting for us. So early for us, looking forward, we would like to look more into exactly in what space edge devices cooperate in the context of substation automation system. I think the next point, I wrote that as well, development of hardware in the loop simulation framework for validation testing. So I think it's good that we have been able to work on this and develop a framework which allows us to do further testing in the future.
Thanks. Yeah, and the last bullet point there, I mean, it has been really challenging, and I think you, Daniel, mentioned that maybe along in the industrial collaboration bullet point, but from a security perspective, it is a challenge for you as well. I mean, a lot of your facilities is security classed, and it's not easy to just come in there and do tests, and it's quite rigorous security issues with that. So what are your thoughts about that? How will you work in the future now that you have tried?
Yeah, and I mean, the world is changing, and there's new constraints and so on security, which is understandable also. But so I mean, we had to do some changes to adapt for field test, for instance, to select, I mean, other substations than was previously planned. But I mean, I think Yeah, so it is a challenge to innovation, but I think it also puts maybe emphasis for us to develop more laboratory environments and have more how to say ability to do certain tests in lab or through these type of collaborations also, where we're, for instance, we can do tests in your North Star network in LTU. I mean, but yeah, I mean, there's no simple answer to this. It's a complicated world. So
yes, and as you said, the world is changing as well. So we get new requirements and yeah, hinders every day more or less. So it's kind of a constant navigation you need to do.
Yeah, but I think flexibility has been a key point for us to try to replan and be flexible and try to find other solutions to fulfill the project objectives. So.
Yeah, and I think you sum it up really good there, because I think that flexibility is kind of the key thing here, that how we have succeeded. Everybody has helped and being flexible in different ways. So, and I think that's one of the success factors actually. So, if we have completely closed doors, then it's difficult to do stuff. But here we find ways all the time. So, yeah. I see that we have some message in the chat, I think, or no. We will move on in the agenda. So now it's a little bit reflections about the future work. I mean, the project hasn't ended yet. So what we still have left to do is to finalize the analysis of the field tests and produce the final report. And then depending on the results of the analysis, we should take the next step. But we have discussed internally within the project group to write new applications. The power engineering group has actually applied for funding and has received a new funds for a new project from Energiforsk. And maybe Per, you can tell us a little bit about that, or Hafiz.
Yes, it's about to make a simulation model of what is happening when the packets are going from through the network, both the package with the sample values or the goose package with commands. That's just to see what is happening and how things are buffered, and what is the consequence of latency and the jitter, which is the variation of the latency. So, and that's in order to see what kind of measures could be taken, and we'll try to use the knowledge that we got in this project with this test in August to see more how to model it in order to see what could be tested next.
Yeah. Yeah, and I think that we will still collaborate within this consortia. We know each other well now, and what this analysis points at, maybe we can do a continuation project similar to this one. We don't know that yet, but when we are approaching the analysis and get the final results, we will know more, I guess. And also about collaboration, we see that especially for the DCC group, you are looking for collaboration within your area as well to continue there. So we have some threads out, and we will, as I said, act upon those when we get more of the final results in place. All right, so now we're at the end of the presentations, and we will open up to questions.